In this video, you will learn about detour proofs and the midpoint formula. So to start with the midpoint formula, anytime you are given two coordinates and you want to find the exact location of the midpoint between those two coordinates, you can always use this formula to calculate that point. So to calculate that x coordinate, you're going to add the two x coordinates of the given points, so x1 plus x2, and then you're going to divide that in half. So then you're going to divide that by 2. That will give you the x coordinate of the midpoint. Then you're going to do the same thing with the y's. You're going to add the two y coordinates together, y1 plus y2, and then you're going to divide that by 2. And that will give you the exact location of the coordinates of the midpoint. So here's a real straightforward example. It says find the midpoint of segment AB, and we're given the coordinates of both A and B. So it really doesn't matter which point you start with, but so if we start with point A, I'm going to call this x1, and then this y1. And then for point B, I'm going to call this x2, and then y2. And I'm just going to plug my numbers into the midpoint formula. So first I'm going to start by adding the x's together, -2 plus 5, and then divide that by 2. And then for the y coordinate, I'm going to add -4 plus 6, and then I'm going to divide that in half. So here I get positive 3/2, comma 2 divided by 2 is just 1. So the midpoint of AB would be located at 3/2, or you could call it 1.5, comma 1. Okay, so let's try this next example, example 2, using our midpoint formula. So go ahead and try this, and then press play after you've gotten an answer. Alright, so check your answer. You should have gotten 1, comma 1/2 as the midpoint. For this next example, it asks you to find the center of circle P, and then notice that QR is the diameter of the circle because it goes through point P. So we know that that center point will be the midpoint of the diameter of that circle. So go ahead and use the midpoint formula to find the coordinates of circle P, and then press play when you're done to check your answer. Okay, so hopefully you got the coordinates of point P to be at 1, comma 2 using the midpoint formula. Okay, now this last example is slightly different because it's asking you to kind of work backwards. It says the midpoint of segment PQ is at 8, comma 3. If the coordinates of point P are 23, comma 5, then find the coordinates of point Q. So this time they're giving us the midpoint, but now we have to go ahead and find the other endpoints. We have the midpoint and one of the endpoints. So one way to do this kind of algebraically would be to call the missing point, we'll call the coordinates of that missing point just x, comma y. And we know the midpoint formula, you have to add the two x's of the two endpoints. So since P and Q are endpoints, we'd have to add 23 plus x, divide that by 2, and then that must equal the x coordinate of our midpoint, which is at positive 8. And then we could go ahead and solve that to get the x coordinate of point Q. Same thing for the y coordinate. We know that if we add the two y coordinates of the endpoints together, so 5 plus y, and then we divide that by 2, that has to be equal to the y coordinate of our midpoint, which is positive 3. So to go ahead and solve this, I would multiply both sides by 2 to get rid of that fraction. So I have 23 plus x equals 16. And then over here I'd have 5 plus y is equal to 6. And then subtract 23, so that x coordinate would be located at -7. And then if I subtract 5, the y coordinate would be located at positive 1. So the final answer for the coordinates of point Q are at -7, comma 1. So just make sure you read the questions carefully in order to figure out whether you are given the midpoint or whether you're trying to find the midpoint, because this is a slightly different problem and it throws some people off on the quizzes and tests and homework problems. So hopefully you have a better understanding of midpoints. Now we're going to move on and talk about a different kind of proof, detour proofs. A detour proof is a proof where you only have enough information to prove one set of triangles congruent, but you have to use that set of triangles to prove another pair of triangles congruent. So let's try this first example together, and then I have 2 more examples in the next video that I'd like you to try on your own. So I'm going to start by labeling the diagram with the givens. Segment SQ is congruent to segment SR, and then segment QT is congruent to segment RT. So based on this given information, I only have enough to prove the large triangles are congruent. So triangle SQT is congruent to triangle SRT, because I can use the reflexive property on segment ST. So let's go ahead and do that. Then I said we can use the reflexive property on segment ST, and now I have enough information to prove those 2 larger triangles are congruent. So segment triangle SQT is congruent to triangle SRT by side. I get those 3 sides. 2 of them are from the givens in step 1, and then step 2, the reflexive property. Okay, so now we have those large triangles congruent. But we want to prove that segment QA is congruent to segment AR. So there's 2 different ways you can go about doing this proof. We can either prove the bottom 2 smaller triangles congruent or the top 2. It really doesn't matter. You get to choose. So I'm just going to choose the top 2, triangle SQA and SRA. Okay, but in order to prove these 2 triangles congruent, I'm going to need something that they have in common with these large triangles. So what segment or angle do these smaller triangles have in common with the larger triangles? We already know that they share these sides, but that's already given that those sides are congruent. So the only other thing that they have in common with the large triangles are these 2 angles at the top, angle at QSA and angle RSA. So I'm just going to call those angles 1 and 2, because now that I've proven that those 2 larger triangles are congruent, I can say directly after that that angle 1 is congruent to angle 2 by CPCTC. Now, once I have those angles congruent, I can just simply use the reflexive property on SA to get the 2 smaller triangles congruent. So I could prove the smaller triangle is congruent by SAS. I had a side all the way back from the givens in step 1. I have my angle in step 4, and then my last corresponding side in step 5 by the reflexive property. So now I can finally prove what I was initially trying to prove, that segment QA is congruent to segment AR by CPCTC. So in order to really complete these detour proofs, there aren't any new theorems that you will need to complete them. It's just a matter of recognizing from the very beginning which triangles you'd have enough information to prove congruent. So we did have to take a slight detour in order to get the pair of triangles that we wanted. So the detour we had to take was proving the larger triangles congruent. That's where the name the detour proof comes from. The only way that I could get those smaller triangles congruent is if I took that detour and proved the larger triangles congruent. So that's where that name detour proof comes in. Notice a lot of times in detour proofs, you do have to prove, or you do have to use reflexive property multiple times, and usually CPCTC multiple times. You can do that in these proofs, and actually you're going to want to do that several times. Okay, so go ahead and move on to the next video, and I want you to try the next 2 examples on your own, and then you're going to check your answers with the video.